This was something that had to be invented for this particular, for this generalization. This is something that was, from the classical case, reinsertion cannot make a forbidden pattern. So, for example, 321 gets created by deleting the second letter. And go that way. If we were starting here, this has a 231 in it, namely at the end, whereas 321 doesn't. And so when we try to do the inverse map and reinsert letters, reinserting the letters could create the patterns that we're trying to avoid. So we need to check both cases. So we've actually doubled our workload when we moved to the dashed patterns case. But these both can be done with finite checks. The computer does that for us. And in the end, we get the following recurrence in general. We've actually now, if you're keeping track, we now can count each of these pieces. We can count this piece and that piece. I'll show how. So, number of permutations avoiding 23-1 of length n. We just look over all possible first letters that can show up. How do we count that? It's a process of trading in one set for another until we can count them all. So this is for n is equal to or greater than 2. When we look over all possible second letters, n. So we add up B as our second letter, so either we form a 2-1 by inserting something less than A, or we form a 1-2 by inserting something greater than A. Based on this bijection here, this is going to be equal to whatever that total is. And this is going to end up being either 0 if A is, A is greater than 1, or if A is equal to 1, we use our bijection that we talked about up here. All right, so this is a nice recurrence. I'm going to refer back to this a little bit later, so I want to write this in one compact location and then save this for later. Putting it all together, n minus 1, 1b, a equals 1, and b goes from 1 to a minus 1, a minus 1, 1, b, and that's for a equals 2 to n. So it's a somewhat complicated recurrence that shows up from this, but not so bad. What we can do is we take this question.
I have a very stupid question.
No.
I mean, so your algorithm finds these recurrences.
Yes, the algorithm finds
this
recurrences.
for 2,700 other.
I've done it for 2,700 so far. I have a batch of 500 in the oven.
And it's a computer, so we don't care. Have you made estimates on the running time and the storage time?
No.
Polynomial in some.
Oh, so I mean, once we get this, once we get the recurrence, they're all polynomial.
Yeah, but finding.
Getting them, it's constant in the search parameters that you give it. But as you vary the search parameters, so it doesn't matter what patterns you're interested in, it only depends what search parameters you enter. How they vary as you enter search parameters, I haven't done it formally, but like checking for gap vectors requires factorially amount of time. You know, as you increase it, it increases very quickly there. For the depth of the scheme, which is the other thing, you can tell it how far to check. That I don't think anyone's looked into as far as how that increases the running time, the deeper you want to go. We just know we don't like looking for prefixes of length 5 or more than 5, you know, and that's where we cut off. But even with cutting off there, we got 2,700 results.
This is perhaps not polynomial low degree.
Yeah, I don't think, no, it's certainly not polynomial low degree.
No, it's exponentially the size of the pattern.
Yeah, yeah.
But so everything else, not bigger.
So yeah, it definitely takes a long time. Anyway, so once we do this, we can run this through the recurrence. If you're interested in sequences, this sequence ends up being 1, 2, 5, 15, 52.
Is it in stone?
That's in slow, and that's the bell numbers. This is the number of set partitions of a set of size n. And partitions. This actually also has a nice combinatorial interpretation in terms of set partitions. This is the number of set partitions where A is the largest partner of 1. Whatever block contains 1, A is the largest roommate of 1.
And did humans have it before?
Yeah. Yeah, I mean, this bell numbers thing was done by Clayson back in 2001, when these dashed patterns started showing up. But,
I can do it with a computer.
but now I can do it with a computer.
And 27
And I can do 2,700 other patterns. So this gets something called Aitken's array. If you look at the triangle of numbers, that that's what it is. It's Aitken's array. That's also its name. So I'm going to take a moment to talk about the general case. Well, it's not even really worth talking about the general case that much. I've mentioned it a lot. We've done this sort of thing for, we've checked something like 6,000 different sets of patterns that we're interested in, and of those, just south of half have had schemes like this. What does it mean to not have a scheme? How does this happen? Well, we got lucky. We got lucky that the prefix pattern 1, 2 has one of these reversibly deletable letters. There's no guarantee you have one of them. So say 2, 1 didn't have a reversibly deletable letter, we would have to move on to a next step. We'd have to look at all permutations that go, instead of 2, 1, we'd have to split that up even further into 2, 1, 3, 3, 1, 2, and 3, 2, 1. They start off with a fall, but then we need to know what the next letter is. And then possibly the next letter and the next letter. So this is one of the search parameters. How deep do you really want to cut? How far do you want to go? And there's no guarantee that it ever stops. In fact, for the classical patterns even, if you look at 2-3-1, you know, only a dash away from our running example, there is no finite scheme. Every time you have one of these decreasing patterns, this will have no reversibly deletable letters, and you'll have to cut it up farther. And so we see 3, 2, 1, we'll have to cut up that farther. And it actually is a never-ending process.
But it's equivalent to something that does have.
But, you know, it's conveniently enough, the number avoiding this is going to be the same as the number avoiding this. You just write your patterns in the mirror. Reverse them left and right.
Probably also in this case you can extend.
Yeah, yeah, and then you can do that. You can do that here. I chose this one. If I wrote this backwards, 1-3-2, that has a much more complicated recurrence. I have to go into step. I have to do depth 3. I didn't want to do that. So yeah, when I say 6,000 different classes, I checked both of these, but if one of them counts, they count as the same class. So I count it as a success for both. So there is no a priori guarantee that you give it a set of schemes and it's going to terminate. We have a busy beaver kind of problem here. But I was able to prove that for certain cases you are guaranteed a finite scheme. And those cases are when you're dealing with dashless patterns, consecutive patterns. The letters all have to be next to each other. You are guaranteed to have a finite scheme, and it's going to stop. Actually, after whatever the length of your pattern you're interested in, you go that deep. Conveniently enough, I also proved that any pattern of the form sigma 1, sigma 2, sigma k, dash sigma k plus 1. This is all consecutive, these are all next to each other, single dash and one tail letter. So 2, 3-1 fits this pattern here. This is also guaranteed to have a finite scheme. As far as I'm aware, this is the first time that we have a systematic method to count all patterns of this form, permutations, counting all of those. There have been ones that this happens to be just a 1 at the end, stuff like that. Elzadi did that a couple of years ago. But this is the first time we can count that whole class of patterns with the same technique. So, in the last 10 minutes, I want to talk about chapters 4 and 5. I'm not going to talk about chapter 2. And what they have to do with enumeration schemes, because they both do. So what chapter 5 does, it answers a major criticism of enumeration schemes. And that is, enumeration schemes can only get you numbers. They only get you the next term of the sequence. But there's a lot of interesting phenomena that happen with those sequences that schemes can't really tell you anything about, at least not on their own. For example, do they fit certain polynomials? The scheme will verify, well, for polynomials you can do, but what about p recursiveness? This is a nice property that sequences sometimes have. The scheme itself cannot imply p recursiveness. It can strongly suggest it, but it can't prove it. It can give you 100 terms of evidence. Another common criticism is you can't get generating functions.
The so-called something called
Right, yeah. P recursiveness is a nice property that sequences can have. It would be nice to show that certain sequences have that. Schemes can't do that, at least not on their own. Asymptotics. Schemes can't really get you asymptotics. Whereas as n gets large, what happens to the sequence an? Again, it gives you strong evidence, and that's
So you're saying you can't take that recurrence there and get a generating function out of it?
I can now. That's what chapter 5 does.
Okay.
No one has done that before. Yes, for this one, since we know it's the bell numbers, we can go through other channels. But we couldn't go directly from the scheme until now. So, let's suppose we have this generating function. And this is z to the n, I should say what my coefficients are. Number of permutations, avoiding 2, 3-1, with pi 1 equals a, and length of pi equals n. So length n permutations, first letter is a, z is going to keep track of our length, x is going to keep track of our first letter. These are formal power series. We're not worrying about convergence, that sort of stuff. Once we have that, I've found a way to use the scheme to get a functional equation. Now, I'm only writing this because to show you how ugly these equations can get, but it's something. And this actually is a fairly tame one. Zx squared x minus 1, f zx 1 minus zx x minus 1, f of zx. What I was able to do is take this recurrence and turn it into this generating function using something called the umbral transfer matrix method. This is another one of Zellberger's ideas that I've been able to prove to another one, apply to another one of his ideas. the idea is that if we're looking at all permutations, and start with a 1, 2, we would restrict this down to just the permutations that land in this set. You can write the generating function for that, the weight enumerator of that, in terms of the original weight enumerator. And this gets you the weight enumerator for this other one. I don't want to go into too much detail because it takes too much time, but you can see that you get these functional equations out of the scheme. And from these functional equations, if you know what you're doing with them, you can get stuff like asymptotics, you can get stuff like closed forms, you can get stuff like recursiveness, holonomicity, being something called holonomic, another nice property. You can get all that sort of stuff from the functional equation that the original scheme couldn't tell you. So it's really a translation. For the last 5 minutes, I'd like to summarize what I do with chapter 4. And it's really a refinement of this. It's something looking at this a little bit more carefully. Let's cut this down so I don't really need it anymore. There's a property of permutations known as the inversion number of inversions. What this is a copy of a certain pattern. Of 2-1. This is really letters pi I greater than pi j for I less than j. Number of times you have a larger number in front of a smaller number. So the inversion of pi is the number of, use that notation. So for example, 31425 has 3 inversions, namely 31, 42, and 32, showing up there. Inversion number is one of these permutation statistics that shows up all the time. Inversion number is the number of times you look at these algebraically. It's the number of transpositions it takes to sort a given permutation into the increasing. But it's a level of disorder. We want this. The number of permutations avoiding 2,3-1 still with inversion number k. And we'll keep track of that, keeping that as the coefficient of q to the k. So we have a big polynomial. These are, I have k greater than or equal to 0. These are polynomials though. So for example, q, and it keeps going, and these are, for example, 1423, 2143, 3124. These all avoid 2,3-1. These all have 3 inversions in them. That's what shows up there. Notice that if we just plug in 1, we just get the number of permutations avoiding in the end. We ignore the inversion criterion. What we can do is we can take this enumeration, we can take this recurrence. I'm going to write it as a recurrence for Fnq. And this is, again, refinement down to all the ones that start with letter A. Replace An with Fn minus 1. So this recurrence is not true as written. But as it turns out, we only need correction factors that are q to a certain power, which can be written in terms of A and B. As it turns out, these deletion maps act very nicely. These bijections act very nicely in terms of inversion. And so you can get nice recurrences for these refined counts. I'm not going to go into it. You can do the same thing for descent number, where it's number of copies of 2, 1 next to each other, number of times you down step. You just get a slightly different recurrence. And again, anytime you have an enumeration scheme that works, you can make this refinement. You can make this, you can look at inversion numbers instead. I'm going to stop at that point. There's a lot more I could talk about, but I don't have time to.
Thank you very much. This ends the public part of the talk. However, we hope to take Mr. Baxter to dinner, possibly Dr. At the Thai restaurant at 7 in Highland Park, 7 p.m. If you'd like to join us, please wait outside until the end of the deliberation of the committee. So, if you don't want to.